Today we have a fun but very tricky problem which will really test your ability to solve differential equations. And the problem is this. There is a river m meters wide which flows at 1 meter per second. We have a boat which can travel at b meters per second, and we want to cross the river and reach the far bank level with the point where we set off. We always aim the boat straight towards the point we want to reach. Given this information, what path does the boat follow? And depending on the value of b, where does the boat end up? Pause the video now and try the problem for yourself. Then I'll reveal the solution in a few seconds. Well, to start off, we'll set the origin to be the point we're aiming for. So that means the boat starts off at m0. And since the boat is always aiming towards the point 0, 0, that means that if the boat is in position xy, then it's pointing in the direction of the vector minus x minus y. Now, the boat has speed b, so we need to normalize this vector so that it has length 1, then multiply it by b. And then we can write down the velocity of the boat in the x and y directions. In the x direction, it's simply the x component of the boat's velocity, and in the y direction, it's the y component minus 1 because of the flow of the river moving the boat in the negative y direction. Now that we know dx by dt and dy by dt, we can work out the gradient of the path, dy by dx, as dy by dt times dt by dx, which gives us this. Now, here we would like to separate the variables so that we have x on one side of the equation and y on the other. But in this case, that just isn't possible, so we'll have to try a different approach. And what we need to do is use a substitution to replace y with a different variable. And if we look at the second term, y over x, that gives us a possible substitution that we could use, as long as we can also write the first term in terms of the same variable, y over x. And can we? Well, fortunately, yes we can. If we divide the top and bottom by x, we get the following expression, where only the variable y over x appears on the right-hand side. So then we can use our substitution z equals y over x, and we can use the chain rule to work out what dy by dx needs to be replaced with. Then plugging that in and simplifying, we have a nice equation where we can separate the variables z on the left-hand side and x on the right-hand side, like so. Now, the next step is to integrate this, and the right-hand side is nice and simple, but the left-hand side is a bit trickier. You could do it by substitution, but it's really helpful if you know your standard hyperbolic trig integrals. And the integral of this is actually arcsine, the inverse hyperbolic sine. And if you want to double check you've got it right, you can always go the other way and work out the derivative to make sure you get what you're looking for, like so. So that's our integral done. We just need to work out what the constant of integration is, and now we can get rid of z and replace it with y over x again. Well, to find the constant term, we need to know a point in the solution, which we do. We know the boat starts off at m0. So plugging this in, we find that the constant is minus log m, which we can tidy up a little. And now finally we've got an equation which describes the path that the boat follows, but it isn't a very nice one. This is called an implicit equation, but we really want it to be in the form y equals some function of x, which is much more user-friendly. And to do that, we need to get rid of this inverse sine and replace it with a log. If you didn't get this far in the problem, this is another good section to try and solve yourself before I reveal how to do it. So again, we can do some working on the side, writing sine out in terms of exponentials. Then this is actually a quadratic equation in e to the v, which we can solve. And we know e to the v must be positive, so we're only interested in one root. And we find that this expression, log of w plus root 1 plus w squared, is an alternative way of writing inverse sine. So we can plug this in Then we want to take e to both sides to remove these logs. And we can multiply by x, bring the y over to the right hand side, square both sides to get rid of the square root, and then just some rearranging, being very careful with the powers of m and x, gets us to our final answer, with y as a function of x. Finally, the second part of the question asked us where the boat ends up, depending on the value of b, its speed. Well, if we look at our formula, the power of x in the first term is 1 plus 1 over b. And as long as b is positive, which it is, this is always greater than 0. So as x approaches 0, this term tends to 0 as well. However, in the second term, the power of x is 1 minus 1 over b. So the behaviour of this term splits into a few different cases. Firstly, if b is greater than 1, so the boat can move faster than the river flows, this power is greater than 0. So y will approach 0 as x tends to 0. So we successfully make it to our destination, and the path looks like this. Next, if b is less than 1, this exponent is negative, and we get that y goes to minus infinity as x approaches 0. So we never reach the far bank, and the path taken looks like this. Finally, if b equals 1, so the boat can move at the same speed as the river, this exponent is 0. So in this case, the second term is just a constant, and the formula actually reduces to this, a quadratic. And letting x equal 0, we can see that y equals minus m over 2. So the boat approaches a point on the far bank, half the river's width downstream from where we set off. Lastly, to help us visualise what's going on, here's a quick animation to show how the path taken by the boat changes as we vary the speed b in a range from just below 1 to just above 1. I hope you found this problem interesting. Since it was river related, I thought I'd leave you with this photo of my dog, Thor, playing in a stream when he was just a little pupper. As always, if you'd like to see more videos like this, please subscribe, or if there's anything you'd like to see in future videos, please let me know in the comments. Thanks for watching, and I'll see you next time.